All right, okay, I'll get started. So welcome back everyone to the fifth lecture in this series on optimal transport. So last time what we did was we set up this machinery of the Riemannian geometric structure of the Wasserstein space. And today is sort of going to be the payoff of that lecture where we're going to see how we can use that structure. So here I just briefly summarize what we're going to do today. We're going to talk about the gradient on the Wasserstein space, and then we'll do the Hessian. So now let's start by formulating some definitions building upon what we did in the previous lecture. So what I want to do now is define for you what is the Wasserstein gradient of a functional. So suppose that I have some functional over the Wasserstein space. So that means it takes in some probability measure and outputs a number. So given this functional, the Wasserstein gradient of this functional, and this is going to be denoted nabla with a subscript of W2F. So I should say the Wasserstein gradient at mu But actually, let me pause here and tell you a kind of a funny story. So one day, my advisor, Philippe, he came to me with a very excited tone of voice, and he said, I just came up with the best notation for the Wasserstein gradient. And this is what he drew for me. So I will not be using this notation, but you might see it in the future. Okay. Anyway, so how do we define the Wasserstein gradient of the functional f? Well, this is actually a general recipe for how you can define it on a Riemannian manifold. So the way it goes is you look at all possible curves that pass through mu. So it's going to be the unique element of the tangent space Recall also this tangent space consists of gradients of functions. That's what we showed last time. So it's the unique element of the tangent space such that for all curves which pass through mu at time 0 with a specific tangent vector with tangent vector v0, I want the following equality to hold. If I differentiate this functional along the curve at time 0, then I want it to equal the inner product between the Wasserstein gradient and this tangent vector to the curve. Okay, it seems reasonable enough. This is kind of taking what we know from Euclidean space and bringing it to a manifold. In the language of geometry, you might say this is the differential of f, and what we're going to do is define the Wasserstein gradient to be the element of the tangent space by using the identification given by this metric. Okay, so this is our definition of the Wasserstein gradient. And once you have the definition of the gradient, we can now define the gradient flow. So the gradient flow is the curve mu t such with tangent vector equal to minus the gradient minus the Wasserstein gradient t at time t. Okay, so also if you remember what it means for this to be the tangent vector to the curve, there were two requirements. The first one is that it has to belong to the tangent space, which in this case means that it has to be like gradient of a function in order to like satisfy this minimal kinetic energy property. The other requirement was that this satisfies the continuity equation, because we said that these vector fields have to explain the evolution of this curve mu t. So if we write down the continuity equation using this as our tangent vector, then this tells us that the gradient flow for f is going to be the following PDE. The time derivative of mu t has to equal the divergence of mu t times this Wasserstein gradient at mu t. Okay, so this equation tells you like what is the Wasserstein gradient flow. At the moment, it's pretty abstract, but we're going to compute the Wasserstein gradient in some concrete examples, so you can identify some dynamics as Wasserstein gradient flows. Now, also, like if you apply this definition of the gradient to the gradient flow mu t itself, then I know that the time derivative of f along the gradient flow has to equal this inner product, but the tangent vector to the gradient flow is minus the gradient. So putting those facts together, it tells you that along the gradient flow, we always have the following. The time derivative of the functional along the Wasserstein gradient flow is always the minus norm squared of the gradient, where this norm squared is the tangent space norm. Okay, so this like also tells you like why we call this the gradient flow. It's kind of in some sense the steepest descent of the functional f with respect to this geometry. Any questions about these definitions? Okay, I also want to give like a little remark, which is, so this is an instance of the continuity equation. And maybe you recall from the previous lecture that the way that we motivated and arrived at this continuity equation was between these two views on fluid dynamics. This is the Eulerian perspective on fluid dynamics, where you emphasize things such as like the mass density and the velocity field. But there was also the particle interpretation, the Lagrangian perspective, which tries to ask like what do individual particle trajectories look like for this equation. So we can ask like now we can go back and ask what's the Lagrangian interpretation of this equation. And because minus the Wasserstein gradient, this is the velocity vector field under which the measure is evolving, then let's say the Lagrangian description is the following ODE. So I initialize my particle randomly according to the initial distribution mu0, and then I follow the ODE where xt evolves according to minus the Wasserstein gradient at xt. Let's like parse this notation to make sure we're all on the same page. So this is the Wasserstein gradient evaluated at the law mu t of xt. So this is like usually where the implementation problems come in for when you want to use Wasserstein gradient flows in applications. Is like this Wasserstein gradient flow is going to depend on the law of xt itself. And then, so this Wasserstein gradient is a vector field, a mapping from RD to RD, because that's how we set up the tangent space. And so we're taking this vector field and then evaluating at xt itself. So through this, like every Wasserstein gradient flow has this like particle interpretation. Okay. Let me write mu t is law of xt. All right, let's be a little bit more concrete now, and let's talk about our motivating examples. Yeah, mu t is the law of xt. Okay, so we're going to show these first two examples are Wasserstein gradient flows today. So the first one is the heat flow. So probabilistically, I mean, the heat flow has many guises, but probabilistically, if we take a Brownian motion, and we also let mu t.
What is the interpretation of this Wasserstein gradient of x?
Yeah, so because the Wasserstein gradient is so this functional is over the Wasserstein space, so I need to evaluate the gradient of this functional at a particular measure. And then once I do that, this gives me a vector field that describes how the particles should evolve. And then so the velocity of my particle trajectory is the vector field at the location xt. Now maybe this will be more concrete when we look at some more specific examples. Okay, so for the heat flow, let me take mu t to be the law of square root 2 times Vt. In which case, like, it's known that the evolution of the law of Brownian motion is just given by this Pd, partial t mu t is the Laplacian of mu t. So this is the famous heat equation. So this factor square root 2 is just so I get the heat equation out. Otherwise, like, I would have to have a factor 1/2. But I don't want that factor half. Okay, so this is the heat equation. That's going to be one of the examples that we show as a Wasserstein gradient flow today. Slightly more generally, we're going to talk about the Langevin diffusion. So the Langevin diffusion, it's specified by a function v over Euclidean space. This is going to be called the potential energy. And given this potential energy, the Langevin SD is the following stochastic differential equation. dxt is minus gradient of the potential plus a Brownian motion. Okay, so the heat equation is the special case where this potential is 0. There's no potential, but sometimes we want to consider like what happens if there's a confining potential. So actually in physics, this is like sometimes called the overdamped Langevin equation, but basically like one of the motivations for the introduction of Brownian motion was to model what like the movement of like particles, like gas particles. So the Brownian motion represents these particles like moving around and randomly due to like collisions with each other, but then you might consider also a potential energy. Yes, question?
So when you say Brownian motion, you only care about the marginals. So let me like just take beauty, Gaussian with variance. You don't look at the marginals of multiple.
Okay, yeah, that's a great point. So the framework of Wasserstein gradient flows is really just describing the evolution of the marginal law. It's not talking about the like joint distribution of a process across different time steps. Although like if I start with this marginal evolution, this particle interpretation gives me one like particular stochastic process, but it might not be the one that I started with. So in particular, note that these are like deterministic dynamics, whereas like the equations I'm going to talk about, like we start off with stochastic dynamics, but nevertheless, like if you just look at the evolution of the marginal law, then you can view them from the Wasserstein angle. I'll touch on that point more later too. Okay, so this Langevin diffusion, if you've never seen it before, let's talk about some basic facts. So the stationary distribution of this diffusion, you can show is the density pi, which is proportional to exponential of the minus potential energy, assuming that this thing is integrable. So it defines a valid probability density. So this is like called like the Gibbs distribution in thermodynamics. It like represents the equilibrium state of your system if this describes your energy function. And so like if you think about what this SD is doing, if I didn't have this Brownian motion part, it would just be gradient flow. And gradient flow is going to converge to like the minimizers of V, or I guess like in the non-convex case to like stationary points of V. But now that I have this Brownian motion, it doesn't just go to the minimizers, it kind of like concentrates around areas where V is small. So that's the intuition, and you get this like stationary distribution, which is like weighted by the value of V. Okay, so this is stationarity, and also from stochastic calculus, there's an equation that describes the evolution of the marginal law of the Langevin diffusion. It's called the Fokker-Planck equation. This we'll take for granted, but it's this equation. Okay, so this Fokker-Planck equation you normally derive via, for instance, like Ito's formula. But this governs the evolution of the marginal law of the Langevin ST. Actually, this equation will be important later, so I'll just copy it down over here. All right, so it's going to be like one of the most celebrated facts of optimal transport that this Langevin diffusion can be interpreted as a Wasserstein gradient flow for a very natural functional. And there's been like many, many more examples of Wasserstein gradient flows. Let me just like list a couple. So there's like more general equations. For instance, like there's these class of like slow or fast diffusion equations. Within machine learning, like there was this theory of two-layer mean field neural networks. In my own work, I've also been using Wasserstein gradient flows to develop algorithms for variational inference. And in general, like Wasserstein gradient flows are just a powerful framework for like developing dynamics to like solve various problems, because you're just finding dynamics which dissipate whatever functional you want over probability measures. And there's like many, many other equations that can be reformulated as Wasserstein gradient flows. You can ask Yair for details like Euler's equations or like drift reaction equations, or yeah, you name it. Okay, but we're going to focus just on these two motivating examples, like heat flow and Langevin diffusion, so we can like really calculate everything. And this is kind of one of the most fundamental examples. All right, so without further ado, I think I'll just jump into the computation of the gradient. Okay, so how do we compute this gradient? Well, we like go back to the definition of the gradient here. What we need to do is say like for all possible curves mu t with a certain tangent vector, we need to be able to compute the derivative of this functional f along this curve. So we're going to start off with some curve that satisfies the continuity equation. And then these v's are going to be like the tangent vectors to mu t. And then we're going to differentiate our functionals along this curve to identify the gradients of these functionals. So normally what you do is like you can define like classes of functionals for which like you can compute the Wasserstein gradient. And actually there's a very like general recipe for like how to compute the Wasserstein gradient of a functional. So it's not like some completely like abstract concept that you can't actually like do calculations with. We'll just illustrate on some like simple examples of these functionals, and then you can compute the gradients of like more complicated ones. So the first functional we'll look at is called the potential energy. this potential energy functional just takes in a measure mu and outputs the average value of the function v under mu, or like v, like we're going to later see, of course, that it's related to this v in the Langevin diffusion. Okay, so this is a well-defined functional over the Wasserstein space. The question is like, what is its gradient? So what we need to do is we need to differentiate the functional along this curve. Okay, so the way that you do it is that you plug in the equation for partial t mu t. So this is minus the divergence. And then you integrate by parts. So you get this. And let me rewrite this as saying that this is the inner product of grad v and the velocity vector field vt with respect to the mu t inner product. And actually, like, if you think about what I just did here, this is like exactly the derivation of the continuity equation. In the continuity equation derivation, we looked at how do the integrals of test functions evolve along the continuity equation, and you get this. Okay, so what does this tell us? Like, if you compare this back with the definition of the gradient here, we do have an inner product under the correct measure, mu t, at time t. And so like this quantity here, this is our candidate for what the Wasserstein gradient should be. The only other thing that we need to know to check that this is actually the Wasserstein gradient is to ask, like, does it belong to the tangent space? In other words, is this the gradient of a function? And clearly, yes. So we know that this belongs to the tangent space. And it gives you the correct derivative of the potential energy for every curve, mu t. So what we've done is we've shown that the Wasserstein gradient of this potential energy function is the following vector field. It's the Euclidean gradient of this potential energy function. And note that this is a mapping from RD to RD. Okay, so that's why, like, when I write stuff like this, I need to like evaluate this at xt, because like what I get is a vector field out, and that needs to be evaluated at a point of RD. Yes. So this functional, the Wasserstein gradient doesn't depend on the measure mu we're at. I mean, maybe it makes sense because this is in some sense a linear functional of mu. All right, so that was easy enough, the easiest example of a Wasserstein gradient. Let's get rid of this. Next, we'll see a more interesting example, which is the entropy functional. Okay, so the entropy functional, h takes in a measure mu and gives me the integral of mu log mu. So information theorists hate me because this is the negative of the Shannon entropy, but this is the convention that we'll use in optimal transport because this is what's going to make it a convex functional, actually. We'll see that later. But now, for now, what we want to do is compute the Wasserstein gradient of this differential entropy. So how do we do that? We differentiate the entropy along our curve. So this is the time derivative of mu t log mu t. Okay, so from calculus, the derivative of x log x is log x plus 1. So then this just becomes log mu t plus 1 times the time derivative of mu t. That's the chain rule. Now we can plug in for what the time derivative of mu t is from the continuity equation. So I get minus log mu t plus 1 divergence mu t vt. And then just as before, we're going to use integration by parts. So I get the inner product between grad log mu t and the vector field Vt under mu t. So again, if you compare with the definition of the gradient, I've again put it in the right form. So this grad log mu t gives us our candidate for the Wasserstein gradient. And since it's obviously, again, the gradient of a function, I know it belongs to the tangent space. So formally, what I've shown here is that the Wasserstein gradient of the entropy functional at mu is the gradient of the log density. Okay, so now, yes, question?
So for the example, the Wasserstein gradient depends on
Yes.
back to the distribution. So what is the initial law of x?
Mm-hmm.
The initial law of x0 is delta measure.
What if the initial law is the delta measure? Yes, that's a good point. Like if mu doesn't have a nice regular density, then this expression for the Wasserstein gradient doesn't make sense, right? So this functional is not really like differentiable over all of Wasserstein space. Yeah, but throughout this lecture, we're just going to focus on like nice enough cases where everything is fine. And then so like, yeah, in this book by Ambrosio, Gigli, and Savary, where they like develop this theory of Wasserstein gradient flows, they have to pay a lot of attention to like, for what initial conditions can we make sense of this Wasserstein gradient flow and regularity issues and so on and so forth. So yeah, definitely check out those references. Okay, so now based on this computation of the gradient of the entropy, let's see our first example of a Wasserstein gradient flow. Let's ask what is the Wasserstein gradient flow of the entropy? It's a pretty natural question, like what's the steepest descent of the entropy functional? So based on the continuity equation, I said that Wasserstein gradient flow satisfies this PDE. It's the divergence of mu t times the Wasserstein gradient, well, let's say like h at mu t itself. But we just computed what this Wasserstein gradient is. It's the grad log mu t. And now we're going to do some manipulations here. So the gradient of the log by the chain rule, this is the gradient of mu t over mu t. The mu t's are going to cancel, so I get divergence of the gradient. But the divergence of the gradient is the same thing as the Laplacian. So in this way, we've recovered the heat equation. And that shows you that the heat flow is the Wasserstein gradient flow for the entropy. In other words, so like I'm asking the question, like if I look at what is like the steepest descent, like what is the fastest way to like maximize entropy in the information theoretic convention, with respect to this geometry of optimal transport, actually it can be realized as the heat flow, which makes a lot of intuitive sense. And in fact, I'm about to state a generalization of this for the Langevin diffusion. Okay, so let's look at, yes, question?
Is there a connection? Is there an easy way to see the Gaussian maximum? Having this kind of result, start Gaussian with a ground motion that is the set. Like fly with the Luca. It's probably much more advanced.
That's a good question. So Gaussians maximize entropy subject to a covariance constraint, right?
Yeah.
So there actually have been some work, there was a work looking at Wasserstein gradient flows constrained to the space of distributions with fixed covariance, I believe. So maybe you can take that constrained gradient flow and prove that fact. I'm not sure, but
also you have all sorts of statements about distributions that maximize entropy or something.
Mhm.
It's again exponential.
Yeah, so I haven't seen a proof of Gaussians maximizing entropy from this perspective, but yeah, I could imagine one exists. All right, so let's now interpret the Langevin diffusion as a Wasserstein gradient flow, and the functional for this is going to be the relative entropy of mu with respect to the stationary distribution pi. So I'm going to claim that if I want to minimize the KL with respect to the stationary distribution, the steepest descent is the Langevin diffusion. So to see why that's the case, let's first write out what the KL divergence is. It's mu log mu over pi. But remember that pi is proportional to x above minus v. So this means that log 1 over pi is like v plus a constant. So if I consider this log 1 over pi with respect to mu, then this is exactly, it's exactly v d mu. And then I have the mu log mu. And then I have this irrelevant constant term. And we can identify the KL divergence as exactly the sum of the two functionals that I've been talking about so far, the potential energy and the entropy. And we've computed the Wasserstein gradients for both of these. So now we can write down the gradient flow of the KL divergence. It's partial t mu t is the divergence of mu t times the Wasserstein gradient, which is just the sum of the two. So there's a grad v and a grad log mu t for the entropy. But the second term, this divergence of mu t grad log mu t, like if you do the same like manipulations we did over there, it will give you back the Laplacian. And we can recognize this equation now as the Fokker-Planck equation for the Langevin diffusion. So this is a pretty important result. Let me write it out for emphasis. So theorem, and this is attributed to Jordan, Kinderlehrer, and Otto. So the Langevin diffusion, the Langevin diffusion is the Wasserstein gradient flow of what functional? It's the relative entropy with respect to the stationary distribution. And yeah, I mean, it's just worth pausing for a moment, just this is such a beautiful result, this geometric understanding of what this Langevin diffusion is doing. And another amazing thing about this, which Otto comments on in one of his papers, is that this framework, it naturally separates out two aspects of this problem. One is thermodynamics and the other is geometry. So the thermodynamics is encoded in the objective function, the relative entropy, whereas the geometry is encoded by the Riemannian geometric structure over which we're taking the gradient flow, Wasserstein geometry, because the Wasserstein geometry is capturing the geometry of Euclidean space. Okay, let me also remark. So this is elaborating a little bit on a remark that I said earlier, which is the Langevin diffusion, we start off with a stochastic differential equation, like this stochastic process. We looked at its marginal law, and then we said the marginal law is this Wasserstein gradient flow. I also told you that every Wasserstein gradient flow can be interpreted as a deterministic particle evolution. So the deterministic particle evolution corresponding to this Wasserstein gradient flow is the following. So the Wasserstein gradient flow is also realized by I just treat the Wasserstein gradient flow as a vector field, and I just evolve my particles according to this. Now, like personally, I'm not such a big fan of this approach, but this approach has gained a lot of traction in the machine learning community, because you look at this equation and then you think like, wow, now we have like some deterministic dynamics of simulating this gradient flow for the KL divergence. Maybe like, since deterministic dynamics are easier to like implement numerically, this will help. But of course, like the issue is here because in order to implement this, you need to know the grad log of the density. So if you just have like finitely many particles, it's like hard to estimate the gradient of the log density. And then so people do a lot of things, like maybe use a kernel density estimator for μt. And this like leads to like other kinds of particle algorithms. So just saying like this is kind of the start of a whole industry. Right. Okay, so now let's try to move on to the second part, which is like, just because I know it's a Wasserstein gradient flow, what information can I like extract from this about the Langevin diffusion? Yes, question? What is Gaussian? So no, this is, pi is not necessarily a Gaussian. It's like any potential function for which this thing makes sense. I can consider the Langevin with that target. So yeah, of course, like one of the most important applications of the Langevin diffusion is I start with this distribution pi that I want to sample from, for instance, like the posterior distribution in a Bayesian inference, or like maybe this is like my multiplicative weights distribution in online learning, and I want to sample from this to like play my next action. There's like many applications of this sampling problem, and the fact that this diffusion is going to converge to this gives me like is the basis for MCMC, Monte Carlo Markov chain methods for like solving this sampling problem, and that will be the subject of the last lecture on this mini course. So we'll see like maybe some implications for what this perspective has to say about MCMC. Yes.
So you mean the
Yes. So the trajectories are not really related to each other. Let me just try to quickly visualize this. So imagine I do Langevin. So this is Langevin. So I start off with a bunch of particles. This is stochastic dynamics, so they're going like all over the place, right? And then, so now if I look at this like chaotic evolution of particles, but try to focus on the evolution of the entire collection of particles at once, then maybe like the evolution of the distribution is like more tame. So maybe the evolution of distributions looks something more like this. So now what I'm saying over here is like, suppose I just focus on the evolution of marginal distributions. What is like a particle evolution that could give rise to this? And because of the notion of like optimal transport that was baked into this, when you look at these dynamics, the particles will like kind of move in a much more orderly way. Like the particles are moving like to emulate this evolution of distributions while also like not making any wasted movement. So that is like one cool thing about these kind of dynamics is if you manage to like implement this and you like just plot the trajectories of your particles, they actually have like very nice movements. All right, so let's move on. So the last thing we want to do is like, what would really tell us a lot of information about the gradient flows is to know whether we're following the gradient flow of a convex functional. As soon as we know that the functional is convex or strongly convex, then we'll get like all sorts of like rates of convergence results for the gradient flow, and also like in the next lectures we'll see how these convexity results can be used to prove results about functional inequalities in high dimensional probability. So let me recall the the notion of convexity. So the following are equivalent. The first is the definition I gave at the very end of last lecture, which is if I look at a geodesic, the functional at the geodesic at time t, it's bounded by 1 minus t times f of mu 0, t times f of mu 1, minus alpha t 1 minus t over 2 times the squared Wasserstein distance, where alpha is like the strong convexity parameter. If alpha is 0, then this is just convexity. So this is the 0th order definition of convexity. It doesn't involve any gradients. But of course, there's like equivalent reformulations of this condition. And I'm not talking about the conditions under which the equivalence holds, but let's say everything's nice. So the first order condition looks like this. I should say, okay, so this is for all geodesics. The second condition is that the above tangent line definition. So for any other measure nu, f of nu should be bigger than f of mu plus the Wasserstein gradient at mu. And then what I would want to put here that's familiar from Euclidean convexity is nu minus mu. But of course, nu minus mu doesn't make sense here. What it really should be is like the tangent vector that starts from mu and points in the direction of nu. So what this is the transport map, the optimal transport map from mu to nu minus the identity. And this inner product is mu, and then I have the extra term from strong convexity. And the third condition is the second order characterization of convexity. So I'll start by putting this in quotation marks. I want the Wasserstein Hessian of mu to be bigger than alpha. But then, like, what does it mean to talk about the Wasserstein Hessian? So I'm going to try to argue to you that one way of getting at this Hessian condition is that I want for all geodesics mu t, if I differentiate this functional along this geodesic twice, and let's say I evaluate it at 0, then I want this to be at least alpha over 2 times the Wasserstein distance. No, just alpha. Alright, so let's just like briefly recall the Euclidean situation so we see what's going on. Let's say that f is a function on Euclidean space and xt is a curve, xt is a curve. If I differentiate this function along the curve, I will get, by chain rule, the gradient and the velocity of x. So this is the first derivative. If I compute the second derivative, then I will get 2 terms. The first is Hessian of f times xt dot. And the second term is gradient times the second derivative of x. Okay, so the point is like, if in order to get at this Hessian term, I don't want this second term. But this second term involves the acceleration of my curve. So in general, this curve will be 0 along a geodesic. And that's kind of the idea behind the Hessian computations we're going to do. We're going to restrict ourselves to like Wasserstein geodesics. And then when we differentiate twice, we will not have this second term. We will only get this Hessian term out. And then to argue about strong convexity, I want to argue that this quadratic form is lower bounded by alpha times like the norm squared of xt dot. So those are the Hessian computations that we'll do in Wasserstein space. I guess maybe I'll keep the entropy here. Okay, so Hessian computations. So what's the setup for these computations? Let's say like mu t is going to be a Wasserstein geodesic. So what is its tangent vector at time 0? At time 0, the tangent vector is gradient psi, which is just gradient phi minus the identity. And this is the Brenier map from mu0 to mu1. Okay, it's like the optimal transport map minus the identity, because when I subtract the identity, I get the displacement that I need to do to move from mu0 to mu1. So this is going to be the tangent vector at time 0. And recall also for Wasserstein geodesics that mu t is the law of xt, where xt follows this McCann interpolation. We just travel at straight lines. And the x0 and x1 are optimally coupled. So x1 is the Brenier map applied to x0. Okay, so that's our setup. So now let's compute some Hessians. We'll start with the easy one, which is the potential energy. So now what I want to do is take that Wasserstein geodesic and differentiate the potential energy twice along it. But this is pretty easy because if I just think about what the potential energy is, this is just the expectation of V at xt, where xt is drawn from mu t, right? So this computation is really just the computation of V, the Hessian of V in Euclidean space. So this is just the Hessian of V applied to x1 minus x0, x1 minus x0. In particular, okay, so the Wasserstein Hessian of this potential energy at mu0. So like what this Hessian should be is it should eat like two tangent vectors and give me a number out. So the two tangent vectors it eats are like the tangent vector grad psi at the start of this curve. So this Wasserstein Hessian evaluated at these tangent vectors is the second time derivative of this potential energy along the curve. And we just said that this thing is equal to, so this thing is grad psi of x0. It's equal to Hessian of V grad psi at mu0. Okay, so this quadratic form for the Hessian is this guy. So in particular, if you just look at this expression, if the Hessian of V is lower bounded, like if V is strongly convex, then this quadratic form for the Wasserstein Hessian of the potential energy, this is also lower bounded by alpha times the tangent norm squared. So as soon as V is strongly convex, then actually the potential energy function is strongly convex over Wasserstein space. Is it equivalent? Yes. Okay, and the last thing I want to do is just to compute the Hessian of the entropy and to show that the entropy is also convex. Okay, so to do that, let's do a little bit of preparation. So this computation is trickier, but not so bad. So along the Wasserstein geodesic, mu t is the push forward of mu0 by this map grad phi t. So what is grad phi t? Grad phi t is the linear interpolation of the identity map and the Brenier map. It's like, why is that the case? Like, remember that we said the Wasserstein geodesic μt is the law of xt, where xt is this interpolation, just following along straight lines. And also, like, x0 and x1 are optimally coupled by grad phi, so this tells you that the Wasserstein geodesic is of this form. So we know that μt is a push forward of μ0 by this map. And since we're going to need to like understand the entropy of μt, we're going to do this through the change of variables formula. So what does this change of variables formula say? It gives you a formula for the density of μt. It looks like this. This is also called the Monge-Ampere equation. Okay, so the change of variables formula tells me after I change variables by some diffeomorphism, then how can I write the density of the new guy in terms of the previous guy. So this, I mean, you can look up later after the lecture if you're not familiar with it. So that's the change of variables formula, and that's going to give us a very convenient expression for what the entropy is. So if I look at the entropy at μt, this is just the same thing as, okay, so this is μt log μt. But I said that μt is the push forward of μ0. So I'm going to apply the change of variables here to rewrite this as an integral under μ0, where I compose everything with the mapping grad phi t. So this is because of this push forward. Now I can plug in the formula for μt composed with grad phi t. It will give me two terms. The first is grad log μ0 log μ0, and the second thing is minus the log determinant of the Hessian of phi t. So now this is very good because this first term is constant, so it's going to disappear when we take derivatives. The second term, the only thing that depends on t is phi t, but phi t depends linearly on t. So now the computation is going to be easy. So I take the second time derivative. And actually, so there's this fact from matrix analysis that minus log det is convex.
So that's μ0 red.
Sorry, where?
That's μ0 red.
μ0 composed with grad phi t. Yeah. So in other words, like μt at grad phi t of x is equal to μ0 x divided by. Yeah. Okay, so actually there's this fact from matrix analysis that minus log det is a convex function over the PSD cone. Also, this guy is linear in t. So this immediately tells you that when I take two derivatives of this will be non-negative. But you can also go further and write down what is the actual second derivative of the log det. And this is an exercise for you, but I claim that it can be written as follows. You get the integral under μ0 of the Hessian of psi. But for us, what will really matter is that it's just non-negative. So this shows that the entropy functional is convex along Wasserstein geodesics. Yes, psi. So psi is grad phi minus the identity. So I want to write everything in terms of psi because grad psi is the tangent vector. Okay, so quiz for everyone. Where in this computation did I use the non-negativity of the Ricci curvature of Euclidean space? Because it's equivalent. Okay, that was obviously a joke, but that's one of the really fascinating parts about this subject is that you can do this computation on a manifold, like a Riemannian manifold, and then the Hessian of the entropy will actually give you a term involving the Ricci curvature. And so it turns out the entropy is convex over over the Wasserstein space over a manifold if and only if the Ricci curvature is non-negative. This was really the birth of this theory of the synthetic theory of Ricci curvature, where here you don't need to talk about a differential structure on your space in order to talk about convexity of the entropy. So this lets you like kind of extend the idea of Ricci curvature lower bounds to more general metric measure spaces. So I couldn't resist mentioning that, but yeah, I think I'm definitely out of time. So the summary is like as soon as V is strongly convex, then the sum of these two functionals, the KL divergence with respect to pi, is strongly convex functional over the Wasserstein space. This is going to lead to a lot of consequences in the next lectures. Yes.
So is there anything here that cannot be achieved? This is a very nice perspective, but does this perspective give you any extra that cannot be achieved?
So it depends on like what particular application you're talking about. In the last lecture of this mini course, I will show you like an analysis of the Langevin algorithm for sampling that heavily relies on this perspective. And actually, like I don't know of another way to get like recover those precise results. Yeah.
You were saying that you didn't like this perspective, and
Yeah.
you said you like better like the but since this equation only describes the measures of the trajectory, is there any special reason to like is there one thing that makes the Langevin canonical? Trajectories of the Langevin?
It's more like I'm thinking in terms of implementability. Like what could be a more useful algorithm for sampling? To me, the Langevin is like very simple dynamics. You can just run it on your computer by sampling some Gaussians and iterating. Whereas like this requires some like heavy machinery in order to try to implement. And then so at some point I start to wonder like, is this really like doing anything that Langevin cannot?
From the point of view of theory, like anything that
The difference is implementability, I guess. Like if I could run this exactly, then like theoretically there's no difference between the Langevin or these dynamics. But the Langevin is, I think, easier to implement. Yes.
So regarding your first question on the derivative
The second, what is the second thermodynamical law? Yes, that's true. Like if you run the heat flow, so the heat flow I said was the Wasserstein gradient of the gradient flow of the entropy. So I also said that along the Wasserstein gradient flow for the entropy, like the derivative is always given by minus the Wasserstein gradient. Right, so because the heat flow is the Wasserstein gradient flow of the entropy, then the entropy is always decreasing along the heat flow. But like decreasing in my convention is increasing in the thermodynamic convention.